like conversational speech, like telephone speech, like switchboard, and library speech, for example, audiobooks and so on. And also, I don't know, like if you, I'm sure everybody, almost every one of you, like looked at the Whisper paper, but yeah, they claim it's competitive or better than human in many domains. And so, yeah, the end of the presentation, basically, it's a solved task. Well, it's not. The fact is that you need to read the fine print, and the fine print is that, for example, for Whisper, they report all the performance with Oracle segmentation and diarization, which is a huge assumption. It helps a lot the system. And in the real world, you don't have Oracle segmentation and you don't have Oracle speaker attribution. So your errors compounds. And another thing is that they report many of the results like on some pretty narrow domains. Like most of the state of the art where the results or where it's competitive with humans is library speech or common voice or Tedlium, where it's not conversational speech in the wild data. And so if we try to, like the results on for Whisper, like the V3 model on some more speech in the wild unconstrained data where multiple speakers can overlap, they can conversate and so on, like CHiME-6, DeepCo, which are dinner party scenarios. So you have a dinner party between friends, like you want to recognize all the speech from far field microphones, or Mixer 6, which is a much easier scenario where you have two speakers, like only conversations, and it's an interview between two speakers. Yeah, the order rates it's kind of high in those cases. So and this is with Oracle diarization. So even this, like this is a CHiME-6 with Oracle diarization and also Oracle. I mean, it's Oracle diarization plus speech separation. In this case, guides for separation. I'll explain it briefly later, but yeah, even with Oracle diarization, you get 36 percent order rate. So the issue is that yeah, it's a multifaceted problem, and you have this long form audio. You need to segment it. You need for each segment you need to find who is speaking, and then you have to do the recognition. So and this can be a few minutes to a couple of hours. So it's not really clear how to handle that, and like you wanted usually to have a speaker attribution of the words and also the start and end of each utterance, at least for actual applications, because that is in many cases what the customers really want. It's like ASR without ASR meeting, for example, without speaker attribution, it would be a bit messy, a bit difficult to use. You can do summarization though. So, and I will explain briefly later about some summarization, interesting summarization results. But yeah, how you deal with that right now is just usually you just do segmentation. So first you do the diarization. You identify segments in this long form audio where the speakers talk, and you for each segment you identify who is speaking when, and then you need to handle the overlapped speech in some way. For example, by doing speech separation. And then once you have the separated speech, you can run your ASR model on each separated stream. This is the one, the most established approach, I would say. And the challenges are like, it's a lot of variability factors, right? Because you have multiple speakers, so the number of speakers can vary between in each meeting. The duration can vary, and if, for example, if you have a very short meeting with lots of speakers, and then you have a very long one with a few speakers, then it becomes very difficult to for the diarization system to handle these two different opposite situations, right? Where for example, if you do clustering, you need to find a threshold that works for both, and it's not easy, especially if you have overlapped speech, and especially if your signal is maybe contaminated with noise and reverb. And the one thing that is often like not looked upon is that the setting and the paralinguistic differences. Like if you have a formal interview between two persons, like a job interview, you can expect that the turn taking is there is not much overlap at speech. The turn taking is more predictable and so on. But if you have like a colloquial meeting between friends, it's like then it starts to be very difficult to handle the overlap at speech, the laugh, and so on. So it becomes much more messy, the conversation, and that is where your system can fail the most. And the amount of overlap at speech can be quite significant. So for data sets like CHiME, it can be like 15%, for example, the development set. So it's quite significant, and it can really mess up your recognizer performance. So the applications for meeting transcriptions are there are many, like of course, like meeting transcription, summarization, also translation, but also of course like data mining for developing spoken language system and so on for LLM training today. But to me, is more fundamental this problem. Like if we want to, I don't know, one day to have really smart agents that can navigate the real world, they have to. We have to solve this problem of robust conversational understanding, conversational speech processing, right? I don't know, I'm thinking about a robot that has to navigate in a restaurant, for example, where there is a lot of background noise, there are many speakers, I don't know, I raise my hand for the order and so on. Or like human-like conversational agents like Moshi, but it can work in a meeting scenario. For example, you have a business meeting with many participants, and the agent understands who said what, when, and it can barge in and provide additional information and so on. For that, we must solve this problem. So I think it's more general in such a way than only transcription. And yeah, like as I explained, like one way to do it is the pipeline approach. And when we run this pipeline, like we do a run diarization, we run speech separation, we do ASR, we end up with a result like that is our hypothesis, like a start time and the words and the speaker for each utterance for the whole meeting. And then we need to, of course, like measure this performance. And we use maybe some metrics that some of you may not be familiar with, because like it's not order rate only. So we care about differences in the start time and time, for example, the segmentation, and also the speaker, like speaker attribution. So the catch is here that it's not guaranteed that your system hypothesis and your reference match. Like not only the words, but also the speaker ID cannot, maybe it's doesn't match. And also the start time and time usually don't match. So how do we evaluate the performance? Because you cannot only just compute the order rate in this case. You don't have an alignment between hypothesis and reference. So you need to find this alignment, and there are several heuristics that can be used to find this alignment. And depending on this alignment procedure, you have different flavors of order rate that one can use. And like, for example, ORC-WHERE, which measure only the recognition performance in this case. So it tries the best possible matching across the whole meeting for each recognized word. The problem is that this metric explodes with the length of the word sequence, so it's not really computationally treatable except for very small sequences. And another one is CP order rate, which instead measures both the word recognition and the speaker attribution. And this finds the optimal mapping between the speaker IDs in terms of the words. So it concatenates the words for each speaker, and then it measures, and then it computes the optimal matching. And then there are time constraint variants of these two. So one is time constrained ORC-WHERE, which measures the word recognition and segmentation, but not speaker attribution. So it cares about the localization, start time and time of each utterance, and also the word recognition, but not of the not the speaker attribution, and then TCP word rate, which measures pretty much everything. So it will measure the word recognition, the speaker attribution, the segmentation, and this is what usually is used right now since the 2 years. And it was originally proposed by Paderborn group. I think Thilo von Neumann he did, and Christoph Bodecker did some work on this. And if we look at the CHiME-7 and 8 DASR challenge, so I mentioned before like CHiME-6 DeepCo. So we tried to build since 2023 this updated CHiME challenge, which basically the idea was expand CHiME-6 challenge and add more scenarios, because our goal was to probe the system to be robust in different domains. And since it's very easy to overfit to one domain, but if you have 3-4 domains, it gets very difficult to build a system that is robust across all. So we collected we used different data set that in this challenge we put together, and the idea is was to diversify a lot the setting. So you have a dinner party, you have Mixer 6, which is one-to-one interviews, and then there is not so far 1, which is office meetings. And then the number of speakers can vary from 2 to 8. And then the duration in minutes it could be 10 minutes to more than 2 hours, for example. And then the recording setup also varies. So you have a 6 linear arrays, 5 circular arrays, and so on. So the idea was try to build a generalist ASR system and try to be robust across these domains. And during the years, like the participants did really good. We had 32 submitted systems, and yeah. By the way, like we uploaded recently. It's in the bottom of this page a preprint of an analysis paper on this. So if you're interested, and yeah, they did pretty great. Like even with CHiME-8, where they had we added another scenario. So not so far 1 was added only on in CHiME-8, while CHiME-7 we had only CHiME-6 DeepCo and Mixer 6 speech. Like they were able to improve further the performance on all the scenarios. So the SDCon team and NTT, they did a very good job in that case. And here we report the TCP word rate across the 3 scenarios only, CHiME-6, DeepCo, and Mixer 6, because not so far was only added in CHiME-8, and across the 2 challenges. And we can see that, for example, like many of the top systems are able to beat Whisper Large v3 with Oracle diarization plus guided source separation, so plus source separation. And it's also interesting the fact that like in some scenarios are still very hard. Like as I mentioned, like dinner party scenarios, like where the conversation is it's very, the turn taking is very fast, and the speech is very colloquial and so on. The TCP word rate is still like yeah, Sunit, sorry.
The baseline, the Whisper Large v3, what is that? Which data set is that on? The baseline which you're drawn?
The base. What I'm sorry. What it was not trained. The Whisper Large v3 here. So.
Okay. But
yeah,
what result is this on? What data set is it on?
This is on across all the 3 data sets. So it's like the challenge was basically across all the 3 data sets, and then the goal was to basically make the participant design a system that was stronger across all the 3 data sets. So it's CHiME-6, DeepCo, and Mixer 6, and the first 2 are 4 speakers. The last one has 2 speakers, and yeah, you can see that the performance still on CHiME-6 is pretty bad. even for the top systems. It's like around 30% still, even for the best systems. While on Mixer 6 with far field 2 speakers is much easier, and then Deepco is in between the two, for example. But yeah, basically they were able to over the year they improve a lot on this case. Most thanks to Target Speaker VAD, to be honest. So Target Speaker VAD was the enabling technology, I would say, to improve on these far field scenarios. And the main findings were even comparing with not so far challenge. So because the CHiME-8 challenge, we also used the not so far one as an additional scenario. We could also compare the CHiME-8 systems, which had to work on 4 different scenarios with not so far submissions, which only were designed for not so far only. And it turns out that these array agnostic generalized transcription systems are quite competitive. So in my case, I think you can probably it's very competitive. So the domain knowledge helps, but it doesn't help that much, I would say. And you can still be very competitive with a system that is general, is designed to work with non-known array topology, for example, non-known domain. And actually, maybe it makes even more robust because the model also has to work on much more domains. So you design the system to be quite robust, and it generalizes very well to not so far one, for example, which is a meeting scenario. And so this was one finding which was surprising to me. I expected, for example, that they will do much worse than submission that were highly tuned for the not so far one scenario, but they did very well. So yeah, they placed second and third, and they were in the top of the CHiME-8, some of the best CHiME-8 systems. And another finding was that the diarization rate is maybe you don't have to worry too much about it, because what matters most is the speaker counting. So if you miss the speaker counting, and so Jacquard error rate, which is more sensitive to speaker counting, it's I think we found out that it correlates more with the TCP order rate, with the final performance. And then, of course, there is a catch. It's because all data participants used a specific pipeline. And so if you use target speaker VAD, and you for example you missed one speaker, or you hallucinated two more speakers than were in the meeting, then you have catastrophic error propagation. And so more than segmentation in that case, speaker counting is quite crucial, I would say. So and in CHiME-8 they particularly focused on this direction because you had not so far meeting scenario, which was 6 minutes, but it can have 8 speakers, and then you had CHiME-6, which had 4 speakers, but it was 2 hours long. And so how you do, for example, speaker counting in this case, and how you make it robust. They developed they made some quite effort on this, very novel clustering techniques, for example, from STCon. So yeah, and I don't know. I think it's worth to check out the system if you're interested, the participants' technical reports about that. And regarding the summarization, as I mentioned before, we found that it correlates very poorly with respect to transcription accuracy. So this is interesting. So if your goal is meeting summarization, maybe you don't care about the transcription too much. I tried to. I made a study on the not so far one scenario, which is a meeting, office meeting, and so we used the system transcriptions from the participants, and then I tried to evaluate the downstream summarization performance, and I used Gemini because it was cheap at the time; it was free. So I prompt Gemini to basically give a summary, but also care about the who said what and proposed idea. So caring about the speaker attribution, because I think it's quite important, for example, in a business meeting and so on. And this was one way to make it to make the diarization and transcription maybe more relevant, and it didn't work. So I tried before, like the most stupid idea, just summarize the meeting, and the correlation coefficient and for between TCP order rate and the summarization metrics. I used the GEVAL and Unival and Rouge. It was bad, but even with this, this speaker attribution with a strategy, it didn't. It increased a little bit, but it's still quite bad, the correlation. And it's interesting to see that, like for example, for GEVAL, which is a metric that is based on that has the most correlation between all the other metrics I tried. So GEVAL is automated metrics that leverages GPT-4o. Basically, most of the system performs equally for most of these GEVAL metrics. Like fluency is about the same because the LLM will make a beautiful word salad that reads very well, and like even if it's not very accurate, the fluency is always high. And but also the other metrics, it's very interesting that even if you take the top scoring systems on the not so far challenge dataset, so it is ESTC NERC sleep, and then there is STCon entity, which was from CHiME-8 DASR challenge instead. Yeah, there is not much difference. And I tried also to do some dummy systems where I do random deletion of 50%, for example, of the words. So you remove 50% of the words randomly, you drop it. It still does pretty good. So it's very interesting. Like only if you make errors in the speaker attribution, then it starts to drop significantly. Like a random speaker deletion, for example. You randomly flip speakers and so on. So it's this, I think it's quite interesting. Like maybe we don't have good summarization metrics, is also possible, or maybe I think like maybe we need to move to end-to-end spoken summarization, because the transcription it's not needed so if your end goal is summarization, maybe you just don't need the transcription at all. So I think that was interesting. And another thing that maybe it's worth to point out is that these systems were mostly very complicated. So even if the end performance was I don't know, better than Whisper with Oracle diarization and so on, they are still very complicated, and they all rely on this pipeline, which is you first do diarization, and then you use the guided source separation, and then you feed the results to a strong ASR model like Whisper. And actually, it's more complicated than that. Like it's a challenge, so most of the participants did ensembles, and I don't know, they had like three different diarization refinement steps, and they try to push every possible the word array down with every possible in every possible way. So I've been like quite obsessed in the latest years to try to make it more streamlined, this pipeline. And it would be cool one day if we have a totally end-to-end system that can take multiple microphones, and then it can handle a long form audio and do speech recognition, speaker attribution, segmentation. We are not there yet. I mean, technically, Gemini can do it, but we done some internal evaluations, like, and it's after 1 minute it starts to hallucinate quite badly. So it's yeah, I think it's I'm not really believing in the fact that you can do with autoregressive next token prediction this problem, but it's certainly one direction. So regarding prime works about this how to simplify the pipeline, like one is of course like var array method, and the methods based in general with continuous source separation. So the idea is just run a speech separation system and get different streams, and then after you can do recognition on each separate stream independently or jointly in the case of bar array plus token level SOT, for example. And the other works is just okay. Let's get rid of speech separation completely, and then just do multi-talker ASR like serialized output training or with permutation invariant training techniques and so on. But all these systems like exec transcribe to diarize, they do not directly address long form. So the problem with long form is that you need a way to keep track of long form speaker identity. For example, across the 2 hours meetings, you need to have your speaker ID consistent in the whole meeting. And transcribe to diarize does that by basically using end-to-end ASR system that's conditioned on speaker embeddings that were obtained by a first diarization step. So it refines. You first run a classical diarization pipeline with the VAD, and then speaker embedding extraction model, like basically a X vector model, and then you use the speaker embedding representation to condition your ASR model. And in this case, it's an ASR model that it's an end-to-end ASR model that jointly model all the speakers. So it's not target speaker ASR like diarization, condition, whisper, and so on. And then you try to refine this diarization and also recognize the speech and so on. So you end up with transcription with speaker and time attribution for the whole meeting. That's consistent on the whole meeting. And in this work, like we published in 2024, I think, like we try to further simplify the pipeline. So instead of having VAD, and then followed by clustering-based diarization, and then followed by speaker attributed ASR, we flipped the order, and basically, okay, let's try to do ASR plus local diarization at a window level, and then do clustering just to basically reassign the speaker IDs and make it consistent overall over the whole meeting. And what we did is that this sliding window diarization augmented recognition framework, where we used an attention-based encoder-decoder model, and we used the WaveLM, of course, like to leverage large-scale pre-training data, because we didn't have much compute at the time. And so this model was trained in the whisper style way. So you basically, the local output was a series of tokens that were okay, the speaker ID, the time, the utterance, the end of the utterance, and so on. And the order of the utterances was first in, first out. And these special speaker ID tokens were only relative. So, for example, like the speaker 0 is the first speaker that starts first in the first window, and speaker 1 is the second speaker in again that starts second in the first window, and so on. But between different windows, they can be different. So in speaker 0 in the second window can be another speaker, for example. And so how we do this? So we need to have a mechanism to deconflict this attribution, and yeah, because like the model, of course, like it cannot be run on the whole meeting, because we will get out of memory errors, and also there will be a mismatch between training and inference. So what we basically did is that we have this model that is composed of an encoder, which is WaveLM based. So we have WaveLM plus I think two transformer layers on top, and then we have autoregressive decoder. But on top of the encoder, we also learn another speaker ID representation head, which tries to estimate the speaker ID discriminative features. So it estimates a vector for a vector representation that, given the time mask and the time average, we can obtain a speaker ID vector. So for each speaker, we get a vector, and then the idea was, okay, if these speaker embeddings are good enough for each window, then we can use clustering to cluster them, and then we can reassign the speaker IDs to be consistent on the whole meeting. And so you will just slide this model like Whisper style, basically. It's like Whisper that also has this chunked inference approach. And you get for each window this local output, and then the speaker ID vectors. And then for the next window, you have the same, but the speaker IDs could be different. And then the idea was you have the speaker for each speaker ID, local speaker ID. You have also the corresponding vector, and then you use clustering and you stitch together everything, because like the clustering will resolve these speaker labels conflicts, and this, yeah.
Sorry, do you have the time information for speaker IDs as well? I missed that in the diagram.
I have time information. So it's for each output, it's basically like the speaker ID, the time, the utterance, and then the end of the utterance. So
I see. Okay.
Yeah. So on each window you do local end-to-end. You do local end-to-end speaker. Yeah.
Hi.
Hi.
How do you when there are overlap, then what will the speaker ID vector look like?
I'm sorry. Can you repeat the question?
I mean, when there is overlapped speech, then which speaker does the vector represent?
Yeah, that's one particular issue of this method. To be honest, we basically rely on the fact that the window is very long, and so during training, the model learns to basically give more weight to the non-overlapped region. But it's unfortunately it's unfortunately a weakness of this method.
Okay, thank you.
Yeah, it's and in fact it works. So in the results, it's basically working quite okay on AMI, but like on more difficult scenarios, it struggles quite a lot. So it's So we trained the model on 15K hours, but with some augmentation of data and the real-world long-form data like CAMI, Mixer 6, CHiME-6, and then lots of simulated meeting data from the NEMO Toolkit simulator. And we also used the standard pre-segmented DASR data. So the model was trained with multitask learning, pretty much. You can prompt the model with I don't know, some task specific prompt, like a token, like a vanilla ASR, for example, and then for that example, the model learns only to do standard ASR, and then you have another modality for which it has to do this end-to-end training, and the results were quite competitive. For example, with transcribe diarize, but for example, the diarization rate was much worse, and also yes, we used less data, but then we leveraged also WaveLM and so on. And the diarization rate was also, I think it's a problem of autoregressive systems in the way that this timestamp prediction, I think it's not it doesn't work really well for diarization, for example. So even the original transcribe to diarize model, it's like the diarization rate is kind of much worse than state of the art, like diarization systems like overlap aware spectral clustering, and our results was even worse. So I think it's a promising approach, but there are some quite some problems also with especially with the clustering and so on. And in fact, like I tried originally to make it work for CHiME-6 data, so that was my idea, and it cannot work. Even on not so far data, when you have 8 speakers, it starts to break. So because also for each window you can have 8 speakers at that point. So this is a huge problem. And the other problem is like you don't have data. You don't have end-to-end. You don't have meeting data for which you have a good annotation. You cannot obtain like telephone, maybe remote meeting data, and maybe podcast. But podcast sometimes it's problematic because most data is not duplex. So you're left with this problem of not having enough data. And one way, and far field meeting data, it's very difficult to collect. Like it requires super complex recording setups where each participant has to have his own microphone and so on. And this is one example from not so far data collection. And so yeah, and for many domains you don't even have any data like doctor-patient recordings, so government and so on. Maybe a few hours of in-domain data. So the whole field relies on synthetic data. I rely that for the slider work, for example, a lot. And like speech separation and enhancement, for example, is the whole field it's mostly done with synthetic data, or even end-to-end neural derivation. The pre-training is done with huge amounts of synthetic data, and so yeah, any multi-speaker stuff you have to use synthetic data basically. So there are many different simulation toolkits one can use. One was the Nemo multi-speaker simulator, which is not working anymore, I think, right now because it has some problems. Like it's broken the code. So I tried it to make it work again like a few months ago because they made many changes to Nemo and it's broken. So and there are different of these toolkits, and they are fast to run, highly scalable because they use LibriSpeech, for example, so existing speech corpora, and then they mix them together. But this will make it non-semantically coherent, the meeting, and the turn taking is quite unrealistic. There are other approaches that try to use TTS, but only in the single speaker case. There are many of those. Like one famous is the machine speech chain, and Sakyani Sakti has many different works in this direction, where the idea is to have this model that is ASR and then TTS and then use and back again. So you basically have you do TTS to help the ASR model, and then the ASR model to collect more data for TTS and so on. And the thing is that this TTS based simulation could have some advantages. So you can control the text, so it can be coherent, the conversation. And also you can modify the text, like for example, you can augment the text. So for some domains where doctor-patient recordings, you can maybe use an LLM to create the content. So I think it's very interesting in this direction. But then it's also slower a little bit, and it's still not realistic enough because the TTS model is run independently for each speaker. Yeah. Yeah. Hey.
Hi, Sam. A question. So the recent
Yes.
progress with LLMs, is it still not possible to ask an LLM to create a coherent conversation?
Yeah.
And then to use TTS in order to actually simulate meetings?
Yeah, it's possible. I think it's possible. This is the advantage of using TTS. That's the thing. The problem is that if you run the TTS for each speaker, it will sound like this.
And thinking, like, what are the chances that he's actually going to go through with this?
It's like, come on, dude. You're an adult now.
Yeah,
act
exactly.
Like one.
Okay, I see.
So that the turn taking doesn't really, it's not really realistic. The content may be realistic, and this content actually was generated with LLM.
Okay.
But the interaction between the speakers was it's not very realistic. So yeah, and what we tried to do last year was with with Jordan Deresky and from University of Rochester. He's a student here, and we tried to use LLM and then a TTS system to generate multi-speaker TTS data, and then to use that to fine-tune Whisper with serializing output training to do multi-speaker ASR. So the idea is like pre-train a TTS system on a large-scale multi-speaker speech corpus, and then use LLM to generate random transcriptions, and then run the TTS, and then try to do that. Try to use that then to improve Whisper performance on some datasets. And the pros is in this case you get semantic coherence because you can use the LLM to generate the both the transcriptions. And you can also get a realistic turn taking if your TTS system is trained on multi-speaker data. But yes, it's of course slower to run that. Yeah.
Have you tried to generate the artificial conversations using real-time models?
What do you mean by real-time models? Sorry.
So there is like OpenAI GPT-4, GPT real-time. They actually.
Oh yeah,
was,
yeah. I think this work was done. I think it was. The problem is that I think it's very expensive. That thing maybe, and I don't know.
Yes.
I think it was done right in the same period when this work was when GPT-4 was out. So but theoretically yes, I've seen people like running, for example, Moshi, 2 Moshi instances to generate duplex data, for example. So it's definitely possible. It's definitely possible. Maybe it's a bit expensive, but it's definitely possible. Yeah. So and in that case also you get these realistic turn taking. It would be as realistic as your model is good though. So and in this work we use the model that called Parakit, and Dia is an open source reproduction of Parakit, so you can try it out. It's basically the same, and they reproduced the Parakit model, which was done by Jordan, and it's an autoregressive model based on the DAC neural codec, and it's conditioned by the text, and the text is multi-speaker text. So the thing is, the model was trained on Spotify podcast data on multi-speaker text. So we used Whisper. So we manually notated 200 utterances and then fine-tuned Whisper to perform a serialized output training with only 200 utterances. And the target of Whisper was like speaker 1, utterance, speaker 2, utterance, and so on. And this worked quite well with only 200 utterance as pseudo labels. And then we trained the TTS model to model 2 speakers conversations. And in our experiments, we basically try to see if this model can help us data augmentation for multi-speaker ASR on Fisher and Mixer 6, which Fisher is telephone and Mixer 6 is far field to speakers interviews. And we used Whisper Medium and then use LoRa, and then fine-tune it to perform again serialized output training now with the TS generated data. And we measured the performance in terms of CP word rate, but not on the whole meeting, this time on each utterance group, because the model right now is it's limited to generating 30 seconds of conversations. So we cannot handle long form generation. So it's interesting that we have a top line, which is of course the Fisher in domain data, and you can use the 1960 amount of hours, and this gets the best performance with Whisper. And without any fine tuning, of course, it's very bad, the performance, because we care about speaker attribution, and the original Whisper cannot do speaker attribution. And then we tried the different baselines. One is the XTTS baseline, that the one that you heard before. So it's the TTS for each speaker, but there is no interaction between the speakers. So you have semantic consistency, but you don't have the paralinguistics, I would say, the speaker interaction. And we did 2 experiments. One is to feed the original Fisher transcripts. Another is to feed the LLM random generated transcripts via Llama 3. And then there was our model, which could do 2 speakers generated conversations. And we found out that it's not like really there, like it's not as good as using 80 hours of Fisher, but you can get somewhat close. Like our best performance was 19%, and it's interesting to see it's much better than using TTS that was trained on basically a TTS that doesn't model the conversational interaction. And also that the content doesn't matter that much. So LLM generated content is actually pretty good. Like if you run the Parquet system TTS simulation on Fisher, and we run it on a random generated LLM transcripts, it's basically the performance on Fisher at the end is basically the same. So the LLM generated transcripts are pretty good for at least for ASR training. And then we did other experiments where we varied the amount of data, and we see that basically there are diminishing returns. That even with 1 hour of data, basically the synthetic speech works as good or even better than the Fisher one. And then with 5 hours, it's Fisher starts to the performance with the original in domain data, it's much better, and then it plateaus the use of synthetic data. And you can see also on the right side where with 160 hours we still have very small gain compared with 80 hours. But another interesting thing is that with Mixer 6, so on Fisher we have lots of in-domain data. We have almost 2,000 hours. On Mixer 6 we have only 2.5 hours training data. And this is much more interesting, because we found out that if you use Fisher, so you use real data from another domain, and if you use this synthetic generated data, it's basically the performance is very close. It's 21 versus 20 for the full Fisher, and 22. It's even a little bit better compared to the same amount of hours. And this was really interesting, I would say, as a result. So the synthetic data works as good as can work as good as real data, but from another domain. And of course, like these are data sets for which you can technically acquire in domain data, but for patient-doctor conversations, you cannot really acquire. So it would be interesting, because then you can use the LLM to generate those doctor-patient recordings, for example. And you can extract the LLM to, I don't know, you can maybe obtain some pseudo transcript from medical reports and so on, and then extract the LLM to generate the transcription for that. And this is one example of the generated conversation with this Parquet model. And the DI is open source. Again, like you can try it. Also, it's similar to Vibe Voice. Vibe Voice also was released by Microsoft recently, and it's also really good. So this is one example.
I'm like, what's going on?
Yeah, like we're sitting there and you're like, what's going on? And I'm like, I don't know, man. I think we're just, I don't know. Like, what are we doing, man?
Yeah, like we're just sitting there, man.
It's much more realistic, like as a conversation. And this makes a difference. So this makes it seems to make a huge difference when you train a at least a multi-speaker ASR model. Like compared to XTTS, there is quite some significant gain. Yeah, I think I'm running out of time, by the way. So I might skip some stuff. How much? I think we are close, right?
I think people start dropping for other meetings soon, but yeah, we are close.
I'm like,
yeah. So the idea was like maybe we can bootstrap this method. Like we did some and we manually notated 200 transcript, then fine-tuned Whisper to get transcript for the whole Spotify corpus, which is not unfortunately is not available anymore. I don't know what happened, but basically they dropped the availability of that corpora, and then we used this transcript to train a TTS to train the TTS system, and then the idea was like, use LLM, get some text, and then generate the TTS conversational speech for TTS, and then use that to train the ASR model. But technically, we can use then the ASR model to filter data on multi-speaker speech, because now we have a multi-speaker ASR model. It's only 2 speakers right now and only 30 seconds, but still. And then maybe you can do iterative pseudo labeling. So once you have a new label speech with this better ASR model, you can just retrain the TTS system again and then iterate again. But yeah, I think it's I think it's interesting approach. To be fair, I think I'm going to skip this because you don't have time. But it was basically about the diarization condition Whisper, which is I think right now it's the best possible model for single channel multi-speaker ASR. Like it's a target speaker ASR model, and the BUT guys they improved a lot recently, and it's open source, so you can probably also use it in production. And we did some improvements during the JSOLT, which basically was to use also enrollment conditioning. And I don't know. I hope the model will be out soon because it's improving a lot compared to the original decal, and Alex Pollock will make it open source hopefully soon. But yeah, and it's reaching state of the art in many different scenarios. Like especially like not so far. It's still far from the state of the art, but on AMI it's very competitive, and yeah, like I don't know, like I ran out of time, unfortunately. So the conclusions for this presentation, it's like unfortunately the modular approach is still superior. I showed this slider approach, and it's really neat to try to make it streamlined and so on. But the modular approach is still superior. Like unfortunately, like for example, decal, I think it's much better. Like it's really robust across many different data sets. Like I mean, not so far with a different number of speakers right now. And the CHiME-8 DASR challenges, which are much more complicated systems. Like of course, it's like decal is just only diarization and then ASR, and the slider try to do everything in one model. Yeah, the CHiME-8 DASR systems are even more robust. But I think it's worth approach, worth research direction to pursue, like to make it something simpler and much computationally efficient. And but the problem is that the lack of data. I showed that you can do TTS, but there are still some problems there, like how you can like 2 speakers you can find like podcast data to train upon. But then more than 4 speakers starts to be very difficult. So we are trying right now to basically take a pre-trained TTS system and then try to extend it to multiple speakers. I'm trying that with one student, right? And one other is pseudo labeling. So there is during the JSOLT we also released and we trained on this 20K hours pseudo label data from Pioneer AI. I think it's open source, but it's It's like a non-commercial license. And yeah, like during JSON also we try to do end-to-end integration of this target speaker ASR and end-to-end neurodialization. It's not working yet. The problem is long sequence modeling. So end-to-end neurodialization, it starts to break for very long data. And we don't know how to handle that. There are some works on NLP that try to do long-term sequence modeling. But diarization long-term sequence modeling is very hard, I would say, because the sequence is starts to be huge, like 100,000 of frames. Or yeah, so it's serious. I think it's a fundamental problem, like in NLP. And about LLMs, I didn't mention them too much, but like I mentioned that okay, with autoregressive models like Whisper or LIDAR or transcribe to derize, the timestamp estimation is very brittle. Like I also observed it on Gemini. So Gemini, after 1 minute, the timestamp will start to drift. I don't know why. So I think it's a catastrophic error accumulation, basically. So he starts to make errors in the timestamp, and the timestamps at the end of the meeting is like they exceed the actual length of the audio, and I don't think it's the right tool for that. So I think that diarization is mostly a local, and ISR also is mostly a local problem, with maybe with some long-term information, but it's basically mostly an encoder problem. And I think it's you need to do integration with an external diarization model. I think maybe it's the best way. Maybe the transcribe to rise way, but instead of using an end-to-end ASR model, you just use a speech LM. Maybe it's the best way. And another thing is that tokenized representation, its neural codecs, is not suitable for much data because they are not trained on multi-speaker data. So they fail. Many of these speech LMs, they fail because the codec representation is trained on music and clean speech. And then you feed multi-speaker data with the noise, and the model starts to hallucinate. But new models like Audio Flamingo 3, they take a Whisper directly, continuous representation as input. So they should not have that problem. But still, they cannot handle reliably multi-speaker speech, which I don't know. Like I think like maybe having an external diarization model, it's right now it's the best way. Otherwise, you're asking for hallucinations. That's what I'm seeing from Gemini anyway. Yeah. Sorry, I was too long, I think. If you have any questions, I'm happy to answer them. But maybe you have to drop over to went. Yeah. Sorry.
Yeah, that's okay. I guess people who had to go for meetings have
Yeah,
dropped
yeah.
out.
Okay.
Thanks a lot, Samuel. Appreciate it.
Yeah, thanks, Sunit.
Anybody has any questions, please feel free to ask.
Yeah, you can just email me, for example. Yeah, or yeah, whatever. It's like I enjoy talking about these problems. Like it's been like my business for 6 years, unfortunately. The multi-speaker ASR, and it's quite complicated.
It is.
Yeah.
We all struggle with it. Well, if there are no more questions, I think we can
Okay.
close this talk, and feel free to contact Samuel. His email is over there.
Yeah, exactly. Yeah.
And again,
Yeah,
thanks a lot, Samuel. It was a wonderful talk. We really
thanks for it.
very
Yeah,
large,
thanks for
very large breadth of topics
yeah,
covered.
maybe too
I
much.
appreciate it.
But yes, yeah, sorry. Yeah. I don't know. I'm happy to answer any question, by the way. Also about DCAO model that I don't know. I can ping Alex to release it because I think that is pretty neat, the new one. So
And
yeah.
you say this is open source and usable for commercial purposes.
The new DCAO, yes. Yeah.
Okay.
It should be. Yeah.
Okay, that will be interesting for us as well.
Yeah, I had to skim through it. The idea is pretty simple. It's just DCAO with also a speaker, optional speaker enrollment, and then so it helps considerably. So we are pretty happy with that result. Yes.
And one quick question for TSVAD, how did you get the enrollment data? Was it eventually done using ground truth, or did you have to estimate it?
No, it's just estimated. Also, for new this decal model is estimated. So
and what do you use to estimate the embedding?
It's I mean, it depends on like are you asking about the CHiME baseline or
Yes.
Yeah. On the NEMO one we use the embeddings from Titanet. Like it's so we use the VAD and then embedding from Titanet and then spectral clustering and then it's basically that is fed to target speaker VAD model.
So
they call
every segment is one speaker. Is that understanding correct?
No. It's just they have to do clustering. So you do clustering, you estimate the speaker centroid, and that becomes your conditioning for they don't call it target speaker VAD. They call multi-scale diarization. Multi-scale diarization. They have the MSD diarization model, but it's actually a target speaker VAD model, and that was one issue with the baseline actually, because the pipeline was too simple for the first stage. So it's like VAD, and then you do VAD, and then for each you do like you extract speaker embeddings for each speech region, and then you do clustering. The problem is that that doesn't account for overlapped speech. So you have overlapped speech, and your embeddings will be contaminated by overlapped speech. And then the model made a lot of mistakes about speaker counting, and you do target speaker VAD, you do lots of mistakes, and then you do GSS, you do another more mistakes, and then that's it. You're screwed up. This worked well for the CHiME-7 challenge, for which there were 4 speakers or 2 speakers. The CHiME-8 challenge had the not so far scenario, which had up to 8 speakers, and it broke completely the baseline. So yeah, the NEMO system was broken by that. The speaker counting, unfortunately, it's a huge issue, and you need a way to if you do like even transcribe to write, for example, will be brittle to that, because if you do vanilla diarization without some overlap where you exclude overlap regions, for example, and so on, you're asking for speaker counting errors because your clustering will make a mess. So that's
what about using END or something like that to get local diarization and then do segmentation? Clustering on top of.
Entity used that. Entity used the end-to-end vector clustering. That worked well. That one works well because it then estimates like embeddings that are overlapped aware. So it uses the segmentation to even Pianote works reasonably for that, because it doesn't it excludes the overlap regions, and you need to do that. Otherwise, you're screwed. And so it's I don't know. But it's interesting that these problems pop up when you try to make the problem harder. Like if you have one scenario, people overfit to that, they will tune the threshold to it's always 4 speakers. You tune the threshold to be robust to that. But then another scenario pops up which is very short with many speakers, and the system is completely broken. So yes, I mean you probably guys are familiar with this because you work with production systems, and you need to be robust to the real world, and the real world is it's not predictable. Yes. So yeah.
Sure. Thank you. Thanks a lot, Samuele.
Thank you for inviting me. Yeah. Okay.
Bye.
Bye. Thank you.
Thank you.